Next, we want to consider a generator connected to an inductor, and we follow the same reasoning as before. Our applied voltage is the same, it's V naught sine omega t, and we're looking for the current. The equation that governs this is the EMF is L di dt. We can then write this in terms of di dt, and we can integrate both sides to find the current. Because we're doing physics, not math, we can just treat these things like fractions and multiply them. And what we get out of this is I as a function of time is negative V naught over omega L cosine omega t. We could again use a trig identity to change this cosine omega t, negative cosine omega t really, to sine omega t minus pi over 2. Now, what's the power consumed by the inductor over a full cycle? Well, again, we can integrate the work or integrate the power with respect to time over one full cycle. And we're going to get some constants, but we can see, again, we're going to have a cosine times a sine integrated over a full cycle. We know that'll give us 0. So, again, the current and voltage are 90 degrees out of phase, opposite direction this time, but that still means that half the time the inductor is taking energy from the circuit and the other half it's giving it back. This, of course, ignores the resistance of the wire that makes up the inductor. If we want to look at our graph like we had before, we have voltage in red, current in green, and power in blue. We see the power is, of course, symmetric, half positive, half negative. But now we notice the voltage is in front of the current. And again, the way we figure that out, cover this up with an index card, slide it to the right. First, you'll uncover a peak in the voltage, the red line, and then a quarter cycle later, you'll uncover the peak in the green. The way you remember this, you can use Eli, where that means the EMF, E, is in front of the current, I, for an inductor. And again, this is by a quarter cycle. If we look at the phasor diagram, we see this same 90-degree angle, now with the current phasor following the voltage phasor. So we know our phase relationship. What about the magnitudes? Well, I as a function of time, we have that for us, and we want to ignore the sinusoid. We just want to look at magnitudes. So we can write I as V naught over omega L, and since V over I gives us our R in Ohm's law, here we can say V over I is the inductive reactance, and we give it the symbol XL. This is defined by XL equals omega L, and of course this is in ohms. What this tells us mathematically is the inductor limits the current at high frequencies and doesn't really limit it at low frequencies. The physical explanation of this is that the inductor opposes a change in current. If you have a low frequency, the current is changing very slowly, or in the case of DC, not at all, and the inductor just acts like a straight wire. If the current is going to be changing a lot, like in a high frequency case, then we're going to have a lot of resistance to that current from the inductor. So we could say in a high frequency circuit, the inductor starts to act like a broken wire, little or no current, while in a low frequency circuit, it'll just act like a regular straight wire, which means maximum current. Now, related to this, a side topic, this is not a course requirement, this is just something that I think you might find interesting. You could spend a couple of semesters of undergraduate or graduate level electrical engineering classes looking at filters, and we're not going to do that. I'm not qualified to teach it to you. But we can take what we just learned and understand a little bit about filters. The whole point of a filter is to exclude some frequencies and to allow some others. So, for example, the largest speakers that you see maybe in the trunk of someone's car, those are subwoofers. And we don't run high frequencies to that because those are too big to move really fast like they have to for high frequencies without using a ridiculous amount of power. We send low frequencies to those. The phone network typically excludes high frequencies because you don't need them in normal conversation, and you can put more calls on a phone cable that way. We're not going to have any homework questions on this or any test questions, but it's just an interesting little side trip here. So let's say now this source represents a whole bunch of frequencies rather than just one. As we send them along these lines, we notice after they get through the resistor, A high frequency would look at this branch here of this capacitor and see that's practically a short circuit to ground, because as far as high frequencies are concerned, this would be very, very low resistance. So the high frequencies would get shunted off to ground, and the low frequencies would continue to your oscilloscope or your subwoofer or whatever you have here. And that's why this is called a low pass filter. It allows low frequencies to pass. What about a high pass filter? Well, if we swap the locations of the capacitor and the resistor, we find that the low frequencies get to this point and they see it like it looks, kind of like a broken bridge. Very, very high resistance to low frequency currents here. High frequency currents would hop right over it. Now, we can also make this out of inductors instead of capacitors, and we would again have to swap things. But this is just the very, very beginning of the idea of filters, if you get interested in that. Now, back to stuff that we do need to know. If we put all three of these things together in an AC circuit, we want to know what the voltage is across each one of them. We know what the current will be across each one because it's a series circuit. So we need to find the phase relationship between the driving voltage of the generator and the current going through everything. We're going to have to add three different voltage phasors, one for R, L, and C, and their lengths depend on the values of the three components here, the resistor, inductor, and capacitor, the frequency of the source as well. So the phase relationships we do know. We already know what that's going to look like. We don't know what the sum of all these voltages, that phasor, we don't know the relationship between the current vector or current phasor and it, but we're about to find it. So we need to be able to add these things that go in three different directions. It's pretty easy to add the VL and the VC part because they're in opposite directions, and all we need to do is give one of them a negative sign. How do we add the resistor phasor to that, though? The problem is it's at a 90-degree angle to the other two, but this is actually something that you solved in about the first or second week of last semester, where you had X components and Y components. They were at a 90-degree angle to each other, and we couldn't add them directly, but we could use the Pythagorean theorem to combine them. Now, our resultant phasor here, we'll call that the impedance, and we'll represent it by Z. It, of course, still has to be in ohms because all the things that go into it are ohms. And all we're doing is R squared plus the difference in XL and XC squared. This is the same way we would get a net displacement out of three displacements to the north, west, and south, for example. Now, you remember this from vector addition, but the other part of it is you have to find the direction that the new vector points, and we had to use the arctangent of y over x to do that. We do the same thing here, where this is our y piece and r is our x piece. So Z is telling us how much current we get in the circuit for a particular driving voltage and frequency, and phi tells us how far ahead of or behind the voltage our current will be. We're going to redo our Ohm's law, and again, as always, not the real law, but the one everybody says is Ohm's law, and say it's V equals IZ. Keep in mind there's no intelligence associated with this. If you put in the RMS current here, you'll get the RMS voltage out. If you put in the amplitude of the current, you get the amplitude of the voltage out. So whatever you put in, that's what you get back. Now we want to work out one of these series RLC circuit problems because there's a really good chance this will pop up on a test at some point. We want to find the current in the circuit, which of course is the same through every piece of it. So if I said something tricky like what's the current in the inductor, well, it's the same as the current in the resistor, the generator, or the capacitor. We also want to find the voltage amplitude across each of these three elements, R, L, and C. We want to find the power dissipated and the phase angle, phi. We start by finding Z, and we have to find XL and XC for that. We know the formulas. It's omega L or 2 pi FL. We put in our component values and our 60 hertz for this generator. So this is 60 hertz with an amplitude of 170 volts. So it's essentially a wall outlet in the United States. When we put this in, we get about 126 ohms. What about the capacitor? Here we have 1 over omega C or 1 over 2 pi FC. We put in our numbers and we get about 177 ohms. Now we have what we need to find Z. We know R already. We didn't have to do anything to find that except read the diagram. We put all this together and we get 95 ohms for Z. This is going to let us find the current. Now, unfortunately, the way I wrote the problem, I left a little bit of a loophole here. You could answer this problem on a test with either RMS current or current amplitude, since I didn't ask you which one in particular. Hopefully on a real test I'd remember to do that. Let's find the RMS value. So I is then V over Z, and I have to use VRMS if I want IRMS. I get VRMS by taking V amplitude, which is what you're given, divided by root 2. Then I multiply by 1 over Z, and I get 1.27 amps. So this is the RMS current. How would I get the current amplitude? I could go back and do this whole thing and just leave this out, the root 2. Or I can take what I've got and multiply it by root 2, and I get 1.8 amps. Now, once I have that, what's the voltage amplitude across each element? We can find the voltage across a resistor using V equals IR. We get, for our resistor, 144 volts. Again, this is the amplitude, not the RMS, because amplitude of the current is what I put in here. Now, some people make this mistake when they try and find the voltage across the capacitor or the inductor. They want to use something like V equals IC. That's not a real thing. That's not a real formula. The units don't work. We need V equals IXC. So we know those numbers. We put them in, we get 318 volts. We do the same thing for the inductor. I times L gives us nothing, but IXL gives us the voltage amplitude across the inductor, and it's 226 volts. Now we can stop for a minute and say, is this reasonable? Have we got a problem here? Because if we were doing the DC version of this, where we had a battery and 3 resistors of different values, it would be easy enough to find the current through here and then the voltage drop across each resistor. And if we added those 3 voltage drops, we'd get the battery's voltage. If we add the amplitudes that we just found for our RLC circuit, we get almost 700 volts, which is way above what the generator's supplying. This isn't a real problem, though, and here's why. We found voltage amplitudes, but these voltages are not all at their peak at the same time. If we picked a particular instant of time, like this, and found the voltage across each element at that point in time, and added them up, we would get the voltage across the generator at that time. So we wouldn't necessarily get our 170 volts even then, unless we happen to catch the generator at a maximum. Now, what about the power? This is where we use the phase angle part. We know if we just had a capacitor, XL would be 0 and so would R. That would give us arctangent of phi is negative, or arctangent of that would give us phi equals negative pi over 2. We also know that circuit doesn't use any power, so our power formula has to reflect that. If our power formula is IRMS VRMS cosine phi, well, cosine phi in this case is 0, so that works. Of course, we can do this with amplitudes, and we get our factor of 1/2 back that we introduced RMS stuff to get rid of in the first place. A circuit with all capacitors would have cosine phi equals 0, so would a circuit of all inductors. This is called the power factor, the cosine phi. So phi is the phase angle, but cosine phi is the power factor. A circuit with just resistors, which would basically be like your toaster, we would have phi equals 0 and cosine phi is 1. Now, why does this matter? Well, at your house it doesn't. A large factory, on the other hand, it does matter. It's typically going to be full of a lot of machines with electric motors, and that means the total load is inductive. It's more XL than XC. Why do they care if their power factor is 0.75 instead of 1? What this means is the factory is asking the electric company to send them more power than they can really use, and then they send some back. But the power company has to build the infrastructure to deliver the unneeded power along with the needed power. So you pay a penalty if your power factor isn't close to 1 and you're a large customer. How can the customers fix this? Well, they could put in banks of capacitors, and that will increase their XC to the point it cancels out their XL and brings their power factor back to 0. If we get to the point where we have XL equals XC, that's resonance, and this is what we had in our tank circuit for our radio. How do we find what the resonant frequency is in general? We set them equal, solve for F, and we would get 1 over 2 pi root LC. This does nothing for us with the factory situation because we can't change F. We know that's going to be 60 hertz everywhere. What we would do instead is put in our known values of L and F and solve for C, and that would tell us what we need to do in terms of adding or removing capacitors to fix this. Now, at resonance, when XL equals XC, that makes Z very easy to compute, and it's just going to be R. This is our smallest possible value of Z at resonance, and we get the largest current there. Now, since the only thing actually turning electrical energy to heat with our ideal capacitors and inductors is a resistor, we could also write cosine phi is R over Z, and since I is V over Z, we could rewrite our power as IRMS squared times R, just what we had before. So kind of interesting. We can do without the Z cosine phi because that's really just R. This is the only place energy is being turned from electrical to heat. Now, the last item in the chapter is an important one. We're going to look at transformers. They should be easier for us to understand and maybe appreciate their importance. There was, over 100 years ago, a large fight about whether city-scale power should be AC distribution or DC distribution. Thomas Edison had done a lot of the invention and financing necessary to bring DC power to small areas in cities and even individual houses that were really more like mansions. And he was very heavily invested in DC distribution. The other side of that debate was George Westinghouse, who was the money guy, and Nikola Tesla, who was the scientist. They believed AC was a better way to do it. And the fight got kind of dirty between them. Edison tried to convince people that AC was more dangerous than DC, and he wanted to get people to start calling being executed in the electric chair being Westinghoused. One of his supporters also traveled around and would go to a new city and execute stray animals with AC systems. One time they even did an elephant. So this was pretty ugly. The problem with DC is not hard to understand. If we have a small power station, like they would have been talking about, let's say it's 100 kilowatts, we can distribute that with any combination of I and V whose product is 100 kilowatts. If you want to do it with ordinary household voltages in the 100-volt ballpark, that would mean you need a current of 1,000 amps coming out of your power plant. If we imagine the wires leaving your power station are so big that their resistance is 0.1 ohms, that's going to be what's called 0000 cable, the heaviest stuff in the Wikipedia wire gauge. I think it's the heaviest stuff you can commonly find at Lowe's or Home Depot. It's about $10 for a meter, so it's not cheap. How much energy will be used to heat this wire up? Well, we figure out it's going to be I squared R, so we do 1,000 squared times 0.1 ohms. That's 100,000 watts. That means everything in your power station is going to go into heating the transmission wires, so that won't work. What are your options? Well, you could use much fatter cable. That's going to be very expensive. That will lower this resistance and the waste heat, but it'll be very expensive. You could instead say, let's distribute at 10,000 volts, because now we only have to send 10 amps of current, and that means we'll have 10 squared times 0.1, or 10 watts heating loss, which is essentially nothing. But nobody wants 10,000 volts distribution in their house. The insulation on the wires, they'd be the size of your forearms or your legs or something. Motors would have to be ridiculously large. The little thin layer of shellac on magnet wire will not be insulating at 10,000 volts. The way Edison fixed it was to essentially have lots and lots of power stations so that nobody is going to be far from one, and this resistance will be even smaller. You probably would not have wanted to live in a place that had a coal-fired power plant on every other block. So AC lets us have sort of the best of both worlds. Let's imagine we have a generator inductor circuit, and the inductor has another inductor, another coil, woven in between, interwoven with it. What we know about our inductors so far is if our coil has NP turns and it's attached to a generator with EMF EP, we could write this equation. The EMF is negative NP d phi dt, where phi is the flux through the coil. We're going to get the same d phi dt through the interwoven coil if they have overlapping areas. We'll call the other one S, the secondary. That will induce an EMF in the second coil, which would depend on the number of turns NS in it. So we have the same formula for it. Now remember, this secondary coil is connected to the load we want to power. There's nothing there but coil and, say, your toaster. But we're going to power it using this changing flux. So if d phi dt is the same for both coils, we could eliminate it and write our transformer equation, which is relatively simple looking. What does this mean? Well, let's say the power plant is generating this power at 10,000 volts. If it's a modern power plant, instead of one of these old ones, it might deliver a gigawatt. That would mean a current of 100,000 amps, which is ridiculously large. We'd never try and transport that. What we could do is connect the generator to a transformer and have 10 turns in the primary and 1,000 in the secondary. Now, what's the output of the secondary? We solve for this ES. We get 1,000,000 volts. Now, our power loss is going to be much lower. Our current will be only 1,000 amps instead of 100,000 amps. If our line is still 0.1 ohms, we know that that means we're going to lose 100 kilowatts, but 100 kilowatts is a tiny fraction of 1,000,000,000 watts, so it wouldn't be a big deal. Now, just like with the Edison case, we can't have 1 megavolt in our houses. What we have to do is use another transformer for distribution around town, and that would be called a step-down transformer. The step-up transformer bumped our voltage from 10,000 to 1,000,000, so we're going to need a step-down transformer, which means we need more coils on the primary than on the secondary. If you have a doorbell, you already have a step-down transformer in your house. It will generally take the 120 VRMS from the wall and drop it to somewhere between 12 and 18. Now you might wonder, how does this coil winding thing work? It's going to be pretty hard to wind two of them to take up practically the same space. It turns out iron will direct and trap magnetic fields, so what we can do is just wrap. This would be our primary, this would be our secondary. We have more turns on one than the other, and this is just an iron core, this simple thing. However, the iron isn't a source of energy. If we step the voltage up, the current has to go down and vice versa. So what we could say when we look at voltages and currents in the primary and secondary coils is EP times IP has to be equal to ES times IS. Now, there are transformers near your house, business, whatever. If you have underground power at home, they're going to look like a big square green box in your yard or your neighbor's yard. If you have overhead power, you'll see a big garbage can-like cylinder on the power pole connected to your house. Now, if you've seen them and paid attention to them before, you might be able to figure out this formula isn't exactly right. You can hear them buzzing, and that takes energy, and if you touch the outside of the case, you'll feel that it's warm. That also takes energy. However, that means that we don't get everything out of the secondary that we put into the primary. Some of it's being lost as heat and this buzzing motion and sound. However, it turns out real transformers are pretty darn efficient, especially the larger they are. Maybe outside your house it should be more like 98% of the incoming power goes to the outgoing power, but still it's pretty good. You may be old enough to remember cell phone chargers back when they were fist-size heavy cubes that some people called wall warts. The reason they were heavy is there was a transformer inside them. If we didn't have transformers, we wouldn't have the electrical grid as we know it, but being able to use them like levers, where we trade current for voltage and then back again, lets us generate at medium voltage, bump it up to very high voltage, low current for long-distance transport, step it back down to medium voltage and medium current. At a few places in the city, they're usually fenced in. You can see they look like something different than a regular business. And then we take that power throughout the city and step it down further at each house or business.